Good morning, everybody. All right, today we have not a Code Forces round. This time it's a CodeJam round. Last time I accidentally called it a Code Forces round when it's CodeJam, of course. Not run by Code Forces, not really associated with Code Forces in any way, other than, I guess, the best possible Code Forces problems are also very similar to the best possible CodeJam problems, in my opinion. I guess CodeJam requires a bit more typing, but yeah, that's all. So this is CodeJam round 1A. So if you're not familiar with CodeJam, there are several different sections. There's a qualification round, which already happened. If you missed that, sorry, you're out. Too bad. Then there's rounds 1A, 1B, and 1C. If you get top some number of 100, I don't know, might be top 1,000 in any of those, you move on to round 2. Might be top 500, I'm not really sure. The goal is like, I don't know, top 100 anyway, so we'll see. Yeah, so if you do remotely well in any of 1A, 1B, or 1C, you can move on to round 2. If you don't do well in 1A, then you get to compete in 1B. So hopefully I will not totally choke in this round, and then I won't be eligible for round 1B or 1C, but we'll see. It's possible I do really badly, and then I'll have the pleasure of getting to be able to compete in another round. I'm going to be using Java here because I want to be somewhat consistent. So yeah, nothing against Kotlin. But my goal is to make to the finals, and I want to be able to do the language I'm most comfortable in for that when it matters in round 3, assuming I get there, assuming I get a t-shirt. All right, so this is 1A. I guess if we have some time, we might as well just check the rules, right? What do we need to? I guess it'll probably say in the contest, actually, right? Yeah. Cool. So here we go. If you're new to the channel, welcome, of course. Fast scanner is the Java equivalent of like doing fast input and fast output, because occasionally using a normal scanner is a bit slow in Java. What else do we need? It's probably a good idea for me to do some thinking on screen. How about that? Because we're not going to be taking this too seriously. It is like a shorter round. It's not a full 24 hours. But I don't expect it to be the most difficult thing in the world. Solving set would be nice. Maybe not 100% necessary, but it'd be nice. And we'll see. All right, if you're doing the round, good luck, have fun. As usual, solutions will be available at the end. And I'll probably put timestamps in the description. I should have time tonight because it's just a Friday evening. But yeah, good luck, have fun, and good morning. Ten seconds. This is like right before a cross-country race when 10, 9, 8, 7, 6, 5, bang, and the gun goes off. It's like you got the nerves. All right, here we go. Let's go. Where are the problems? Let's see them. Problems. Or tasks, if you're Polish. Please give me the problems. Come on, this is not okay. This really gives you an appreciation for Code Forces servers when they can handle it this well. For context, I am in a very heavily populated city that has a Google headquarters probably 100 meters away from where I'm living, and I have 100 megabyte per second internet speed. So it is definitely not my fault that these problems aren't loading. Okay, here we go. Okay, these should be buttons, so I can open a new tab, please. Anyway, we have a list of integers, x1 to xn. We would like them to be in strictly increasing order, but unfortunately we can't reorder them. This means usual sorting algorithms will not work. Our only option is to change them by appending digits 0 through 9 to their right. If one of the integers is 10, you can turn it 100 or 109. What's the minimum number of single-digit append operations that are necessary for the list to be sorted in increasing order? All right. 3 up to 100 elements. Okay, so you add 2 zeros to this, and then you add 3 zeros to this, or you add 2 zeros to this, yeah. So you have 100, 700, and then 1,000. Strictly increasing, gotcha. A greedy approach should work, right? So the first element you don't touch. The second one, you touch as little as possible. And you just always go to the last item if you can. All right, so how exactly does this work? Let's say you've got these 3 digits, and then you place, like you've got 3, so that's the previous number. We know what this number is. If it matches, then we add 0. What if we have just XX? Then we either add plus 0, 0 if this is a 9, or we add plus like x plus 1 if we can do that. Okay, that's if we have a prefix. Oh wait, yeah, okay, if we have a prefix of the previous thing, you add 1 to the suffix. This is kind of annoying. Okay. All right, so I understand the problem. The way scoring works in CodeJam, it's only your last submission that matters. So I'm going to read other problems first and then come back to that in a minute. Because I'm confident I'll solve at least, I think I'll solve at least partial points for at least 2 problems, so it doesn't hurt to read other things first. Two-and-a-half-hour round, okay. Divide the cards into 2 groups in such a way that the sum of the numbers in the first group is equal to the product of the numbers in the second group. Each card has a prime number, okay. Maximum score. What is the score you can achieve? Your score is the sum of numbers in the first group or the product. Or 0 if you cannot split the cards in this way at all. $499, okay. Gotcha. So in this case, the sum goes up to 100. In this case, the sum goes up to 10 to the 5th. Oh, do they have how many of each card we have? You have this many cards of this value, I see. All right, that's a bit tricky. I guess importantly, the sum isn't going to be that big, which means the product can't be that big. Right, like the product's got to be relatively small. So that puts a limit on the number of sums you can check. Okay, so yeah, so the first 2 test cases should be pretty easy. It's the third one that'll be tricky. Let's read this. You've got an exam with Q true or false questions. The correct answer to each of them is either true or false. For each student taking the exam, selects either true or false for each question. The student's score is the number they get right. There are n students who have taken this exam. For each of those students, you know the answers they gave to each question as well as their final score. Assume that any sequence of answers is consistent with all of the students' scores, has the same probability of being a correct sequence of answers. You want to maximize your own expected score. Determine what the expected score is and how you should answer your questions in order to achieve it. Gotcha. The number of students and the number of questions respectively. Contains a string and an integer. Wait, what is n? N is only up to 3? I should maybe mention that. Okay. Up to 3 students, and how many questions? 120 or 10. Okay. Each of the next n lines contains a string and an integer. Students' answers and their score. You have 1 student, 3 questions. FFT, they get 3 right. Okay, what do you print? You print FFT. You expect 3 to be right. Okay. They get FFT and they get 2 of them right. Yeah, so you want to do the same thing because, yeah. Okay. This is kind of funny. It's FFT. I like it. This person got 4 of his questions right. This one only got 2. Interesting. It's kind of tricky. Okay. So it seems like this is going to be a messy, annoying contest. That's my initial outlook on it. The pen sort doesn't seem too bad. Seems like that's going to be the easiest of them. What does Scoreboard say? Looks to be the case. Yeah. So let's do that. Okay. So what do we need to do here? It's probably helpful to have a method that gives us the next integer, right? So static big integer get next, big integer previous, and then int base. Okay. So we'll start initially having the value of the first thing in the array. What Java 11, good. So we'll have big integer stuff that we need. We'll start with just the first element in the array, and then we need to get the next element. So big integer next will be get next. We have this. We're looking at a at I. So we need to get something bigger than at, adding to a at I. Then we need the number of characters we added. So int added will be next dot to string dot length minus a at I plus a space dot length. Kind of hacky, but it works. And then ans plus equals added. And then add equals next. Okay. So all we need now is to finish this method. So how do we do this? It's a bit annoying. It shouldn't be too bad. Okay. So if we're already bigger, just return us. And return big integer dot value of base. Okay, so now otherwise, there are a couple cases, oops. Otherwise we need to be at least as long as it. Yeah, okay, so basically we just want to say if we add 9s until we're its length, will we be bigger? Only up to 100 things, so I'm not worried about time. So while base string dot length is less than brief string dot length, base string plus equals the character 9. If integer, or if compared to previous, if this is greater than 0, then return prev.add 1. Okay, so keep adding zeros till we don't need them anymore, and then return big, or return new big integer base string. Good, okay, cool. So let's try this. 3, no, we got this wrong, okay. 101, not true. Yeah, so this is wrong. This is wrong. Yeah. So we want to add a matching character at each step if we can. But like the prefix has to be base string. Okay. So base string equals base plus this, while base string dot length is less than Oh, okay, we just want to see, this is messy. Yeah, this is annoying. If the prefix matches, add 1 to the suffix. Otherwise, the first difference is in the prefix, in which case, if the first difference is in the prefix, then just add all zeros. Okay. So if prev string, it starts with the base string, in this case return prev.add big integer.1. Otherwise we already are different. So yeah, so while base string.length is less than prev string.length, base string plus equals a 0, and then return big integer, whatever this is. Good. All right, let's try this again. So we get 700 and then 1,000. That's right. Yeah, 4120. Seems to make sense to me. Let's submit this. Wait for a verdict, I guess. And everyone in the world should have solved now, I bet. Lots of solves. All right, we got it. Good. Prime time. Omnic. Why am I not following Omnic? What am I doing with my life? All right, prime time. So, yeah, should we be concerned about this test case 3? Should probably think about it for a bit. The question is like, camera is kind of high up. I don't know how to lower it. What am I doing with my life? Anyway, all right, I guess I'll just have to be like that. Yeah, so the numbers are, we have 2 2s, a 3, and 2 5s, right? 2 2s, a 3, and 2 5s. Product here is probably going to be 10. Yeah. 2 times 5 is 10. So the sum, yeah, if you pick some numbers, the numbers you pick are probably going to be, like, there's going to be not that big of a range of numbers you pick. If you want the numbers you pick to have a very small product, they'll have a, like, 2,000 maybe. Well, okay, what is this? So 500, you pick 500. 499. So you can pick 499. 6 times. Five and a half times. So 499 times like 5.5, maybe. Let's just say 6. So that's about 500 times 6. So there are about 3,000 different sums you could be. 3,000 sums. There are 3,000 possible sums. Okay. What's the follow-up? So for each of these 3,000 sums, for each sum, we want to know what is the product of elements. Yeah, so suppose we know, if we know the sum, right? If we know the sum we're going to use, right? So let's say the sum is going to be x. I don't know why I keep saying right. I'm not talking to anyone. I'm talking to myself. Let's say the sum is x. Like x is what you want the numbers you pick to add up to. So they add up to x. The question is, can you pick numbers which add up to x and then multiply to y? If you know what they add up to, you don't have any choice because each of these numbers are prime. So you have to take the number if it's divisible. Yeah. So it's going to be order 3,000 times 500. Maybe times a log, or maybe plus a log. Should be pretty easy, I think. All right, let's start coding it and find the flaws in our logic as we go. How about that? What could go wrong, right? Usually this is a terrible strategy because there's probably some minor issues with my logic and it's faster to find them on paper thinking about it than in code, but I don't know. We've got 2 hours remaining. What could go wrong? Okay, so this is how many different types of primes there are. Five different types of primes. So one type of prime at 17. Okay. Yeah, let's slow down a minute. So what's our strategy? We brute force what this adds up to. Okay. we have each of these, we have what the prime is and how many times it accrues. Okay, so int prime. So what is this? This is like the max sum of the products. Let's say it's 3,000. Oops. Okay, we also want sum equals 0. And then we probably also want the best answer, which is 0. We'll print that at the end. Okay. Ooh, the number of times we pick something might be a long. That's an easy thing to get wrong. Okay. And we want sum plus equals primes at I times at I. So we have the sum of everything. So this will be product side sum from 1. Product side sum is less than the max that we decided. And have an increment. So this is the sum of things on the product side. So now what we want to see is, can we like pick things to multiply, which sum to product side sum and multiply to the right number. That's the question we're answering. So long remaining sum will be sum of everything minus what we picked to be on the product side sum. Okay. Long to divide out equals remaining sum. It's kind of just long variable names, but we'll figure it out. Okay, so now while to divide out, or I guess, yeah. Modulo primes at I, well, this is equal to 0, then we actually want to divide it. So to divide out divided by equals primes at I times taken plus remaining sum. Oh, I guess we need the sum used. Okay. Long sum used equals 0. Sum used plus equals primes at I. Good. Okay, so if we've used too many of them, we have a problem. If times taken is bigger than how many times we have this, then continue outer. When else do we have a problem? If the sum we use doesn't end up being the right thing. Okay, so otherwise we use a few enough number of each thing. the sum of things ends up being right, and then also we have all of the factors we need. If all of those are the case, then we can use this. Nope, 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 nope. Remaining sum. Okay, I think that's it. Failure. Why is that a failure? Okay, so let's just look at this first. Well, let's look at this test case, maybe. Don't you love hitting magic keys that do things you're not aware of? Run problem B, please. Okay, infinite loop somewhere. N should be 1. This should be fine, I think. Divide by equals primes at I. Oh. Okay. We're saying 17 is the answer. Oh, yeah, because we have 2 of them. Good. Interesting. Surprise. 25, 17, 0, 8. Okay, are there any multiplies that could go wrong here? What's the runtime? 3,000 times n. 3,000 times log, right? Yeah, 3,000 times n plus 3,000 times log. Let's make it 5,000 just to be safe, or 6,000, that's fine. Yeah, I think we should be fine. I think this is right. What's visible? How badly? Ooh, the one hard case. Okay, well, we'll submit. Let's see. We read in longs, I think. This is a long. Yeah, I think we're right. But this is a very easy problem to fail system tests on. So maybe before we quit, we'll come back and look at this. All right. Compile time error. Genius. Galaxy brain submit right there. Okay. Yeah, probably right, but we'll see. Possible there are long issues. All right, final problem. How do we do this? So importantly, you've got 3 people and 120 questions. No interactive problem today. I guess that makes sense. Interactive problem. It's probably a good decision. Interactive problems take a lot of time to do, and only 2.5 hour round, right? So, yes, that makes sense. Okay, so we have some people answer some questions and get some scores, and now we want to say, what do we need to print here? The maximum expected score, and also as a fraction. All right, question of the day. Is the denominator ever not 1? So let's say you have one person, right? If you've got one person and they say like true, false, well, if you have one person, they might as well just say true for everything. Because if they say false, you can just invert everything for that problem. So if you have one person, if their score is equal to 50%, then it doesn't matter. Then who cares? If it's less than 50%, then we pick all falses. Otherwise, if it's greater than 50%, we pick all trues. Okay, that's one person. What if we have two people? Let's just do 3 of these, for instance. So the first person picks all true. We assume there is some answer. There exists one sequence of correct answers consistent with the input. Yeah, okay. There are only 4 different. Either they answer the same or they answer the opposite. So for 2 people, there are only 2 different types of questions. There are questions where they agree. Either they agree or they disagree. With 4 people, there are 4 different types of questions. First 2 people might agree or disagree, and then the first and third person might agree or disagree. Those are independent. So there are 4 different types of questions. Okay, so let's say what if we did, like, what if we do a DP here to like consider all of the possible answers? In that case, what matters? Which question we're on? And how many? Oh, the 3 scores, like score 1, score 2, and score 3. So that would be in the DP. It's a little dangerous. 30 seconds for 2021 test cases. So we would need to do this DP in a smarter way, I guess. What would this equal? We might be able to remove this, maybe. Well, I'm not really sure. I don't really know what I'm doing with this yet. So, okay, what would this DP, what are we trying here? For the DP, we might want to do some sort of thing where we figure out like what let's look at the second case. No, that's boring. Third case is interesting. What is our DP trying to maximize? How many things there are where that's the case? Number of ways it could happen. We want to know which way is the most likely, or like what is our chance of winning if we pick a truth here? So hypothetically, we have a bunch of answers for this person, a bunch of answers for this person, a bunch of answers for a third person. I guess maybe we'll just do 2 of these for now and think about it in a bit. A bunch of answers for Alice, a bunch of answers for Bob. And we're looking at this right here. So we want to say, if this is true, like how many ways could this be true? How many ways could it be false? Would you ever want to pick incorrectly? Would you ever want to get a question wrong? Probably not. Probably pick whichever's more likely. If it's true, then we go to the next question for both of these, and then we adjust their scores accordingly. So we need the question, we need score 1, and we need score 2. Does this have a hidden verdict too, or no? It does. Oh my goodness. Well, yes, test set 2 doesn't matter, but test set 3 is kind of annoying. Because, like, yeah, this might introduce a bunch. Having a third person might be very helpful. There are additional test sets. Is it like that for every problem? No, okay. Easy to miss. All right. What if there are multiple possible answers? Okay, so presumably yes. Yeah. Okay. Yes, that's fine. All right. So if there are multiple answers, we can print any. Yeah. So I think I have test cases 1 and 2 solved probably. Right. We can do a DP where we store which question are we at. What's the score for 1? What's the score for 2? This equals the number of ways that this could be the case. Problem is, this might not be an integer. Might be a fraction. Is the number of ways to do something always a power of 2? No, because you can have something like this. You can have true, true, true. If you get 2 of them right, there are 3 ways. It's 3 choose 2. The number of ways can also be huge for test sets 2 and 3. All right, so we aren't actually getting anywhere with this problem. That's fine. Let's think of some new ideas. With our 48 milligrams of caffeine. This has all been DP approach so far, right? Yeah. Have we used the fact that there are very few types of questions? Every question is either an agreement or a disagreement. Yeah, maybe if the fact that n is really small is significant in ways other than bounding the runtime. So if you have 2 players, if you have like an agreement, then they can either both get it right or both wrong. If they disagree, that means one of them gets right. So there are only 2 types of things, right? If they agree, I guess you just want to see, maybe you want to see collectively, are both of them together better than average or worse than average? Yeah, okay. Are they better than average? Yeah, okay, so like I guess one thing to keep in mind is that if someone is really stupid, that's equivalent to being really smart. If they get everything wrong, you know you could get everything right by flipping all those answers. So you can assume everyone does. Yeah, so if anyone does like worse than half, you can flip all of their answers. If they disagree, do you always trust the smarter person? I think so. I think it's right. I don't really have a proof. So yeah, if they agree, then just, yeah, then take it. Take it. Otherwise, trust the smarter person. This is equivalent to just trusting the smarter person in all situations. Right? It's just trust the person who's smartest. Yeah, so it's like if you have someone who's really stupid, then make them smart by inverting all their answers. After that, just copy the smartest person. Let's see. Okay, yeah, interesting. Looks like you definitely need big integers. Is this like, is this breakable? Does this sanity check? Copy the best person, even though we have more information. Right? If we're going to blindly copy the best person, even though we know other people's test scores, well, I guess with two people, right? If this one gets this one wrong and all of these right, there's no way, like, with a bunch of people, this definitely is not the case. With a bunch of people, copying the smartest person doesn't work. Well, all right, hang on. Let's chill for a minute. If you copy someone exactly, you know exactly how many are going to get right. So it's always an integer. So this is not an integer, which means this they did not copy. Right? There's some non-determinism here. Yeah. So it doesn't work for 3. Here's a break case, but it's completely unintelligible. For 2 people, seems reasonable enough. Okay, so how many points are we missing then? I guess doesn't matter, right? Like, we're in 132nd place. Maybe some people didn't get this. Maybe I didn't get it. But this is, all right, 25 points is pretty important. So, yeah, maybe we should, oh man, it's so tricky. Do I go for 25? What's the idea? What would we do? Some sort of DP. So we have the 4 types of questions. We have score 1, score 2, and score 3. We assume, oh, do we just take the majority for each one? Ugh. That is so messy. Do we really want to do that? Can we, in a group of 3 people, can you detect the majority being wrong? Maybe. Okay, no matter what happens, we need some way of calculating. We need some evaluation, right? Like, yeah, whether I'm being an idiot and completely ignoring the right solution, like no matter what it is, we need some way of like evaluating what is the chance it'll be right. Like, what's the expected number of problems we get right? So how do we do the evaluation? Let's focus on that. Maybe we just take the majority. No, that's not right. Nope. Because if someone gets 100%, then you listen to them even if they're in the minority. Okay. And also listening to the smartest person is wrong because from the sample. Do you always do one or the other? Maybe. Maybe. Maybe if the smartest person agrees with someone you do, there are a lot of things you can do. How do you evaluate? Okay, so we want to know how many ways work, and also how many do we match everybody with. Or like how many, wait, we want to know how many ways work. And how many, not how many do we get exactly right, how many do we, yeah, what's the expected number of questions we get right? I guess the total number of questions in all ways is what we're looking for. Total right across all ways. Okay. So we have, oh, but, yeah, if we can construct the answer, we don't need to pass our answer in if we're constructing it. The position, did they put some in this? There are no constraints on this. So many test cases. So little time. Okay. We need the position, and then we need what the three scores are. We need score 1, score 2, and score 3. Each of the moves are, or each of the edges are independent. They're not really edges. Each of the questions are independent. That means for each group, you always answer the same. Gotcha. Yeah. So there are 4 groups, right? So there are only 2 to the 4, which is equal to 16. Is that right? 2 to the 4 is 16. Yep, 16 possible answers. So we just need to evaluate each answer. Cool. All right. Boom. We solved the problem. Good. How do we evaluate a solution? In other words, we've gotten nowhere, but we've realized we don't have that far to go. It's kind of deep, isn't it? We've accomplished absolutely nothing, but yet we've made so much progress. Yeah, we can't even answer the, I guess like we could, if it came down to it, we could get these points if we needed them to at least look good until the clock ran out and it's revealed we don't have either the 6 or the 25. How do we evaluate this? So it's tricky because you need to pass in our scores as well. So we need, okay, so there are, what's the question here? The number of ways that this could be right. The number of ways we could get like some vector, some like ABC. Sorry, my face is probably blocking part of this, but we want to know this. If we see everything where they all agree, we can either add 1, 1, 1, or we can add 0, 0, 0. Really, we can make a graph here. So we could do a graph. And then the number of ways to get to some ABC is just the number of paths in the graph. Assuming that they don't kill us on test cases. Yeah, so what is your state? It's like score 1, score 2, score 3, and also the question, which is killing us. It's actually just killing us. Let's not worry about multiple test cases. At the end, maybe we'll find some way of handling that. It's going to be close. I don't know if I'll be able to solve this, interestingly. Okay. So we have the 3 scores and how many questions there are. We can... like, we always add 1 to this. But like maybe we add 1 to these 2 scores. Or maybe we add 1 to the inverse. Or like the complement, I guess. Wait a minute. How many types of questions are there? Okay, so there are 4 types, right? So 30 to the 4 possible quizzes. Possible quizzes, yeah. Like for each question, this is worst case. Yes, this is going to be not that big. Oh no, times 2,000. Maybe that's okay. There are this many possible quizzes. Okay. Why is that? Because there are 4 types of questions. And then for each one of those questions, we just care about the size of each set, and then we can do combinatorics to say how many ways that will happen. Yeah, okay, all right. We're making progress here. So there are 30 to the 4 possible like results. For each result, we have 4 questions. There are different sizes. Okay. All right, what do we do now? So for each of those quizzes, we can evaluate the score of, yeah, so we can easily evaluate the score. We can evaluate the score to a lot of things. To each of the originals and all of these. Okay, yeah. They make any guarantees about the input here? No. Oh, but we can, okay, so if we know, yeah, so we can make this better. We can make this 30 to the 3rd. Okay, I think I see where this is going. All right, so we've got like 8 minutes to plan this out, and then we have an hour to implement it. I think that's reasonable. Maybe 10 minutes and then 58 minutes, how about that? Okay, so here's the idea. We have 4 types of questions. Each of those questions, we have a certain, like 4 types of responses. There are 4 types of responses. For each type of response, we have a certain count for each of those. We'll take the one that occurs most and make that a bit special. So now for each of the other ones, we want to know how many times the majority was right and how many times the majority was wrong. If we know that, we know how many points to assign each person. So we can figure that out for the first 3. Then for the 4th person, we can use math. So we know what the 4th one is, because that for loop is only going to be true once. So we know how many points we need to give, etc. Okay. So we're iterating through all of the possible quiz types. 30 to the 3rd. Okay. Yeah. So these are all of the possible things the quiz could be. We need n choose k to figure out the likelihood of each of those. We need big integer because this is going to be absolutely impossible. How big do the numbers get? 30 factorial? It's kind of big. Kind of big. All right. Yeah, okay, so then what are the choices we make? We say for each of these, we're either in the majority or minority. Yeah, okay. Oofda, this is gonna be messy. I said that about A and B, and to be fair, I guess they weren't that bad. B was not bad. A was a little caseworky, but if you remove the comments, wasn't really that bad either. Okay. This one, yikes. Okay, so start with the number of people. Then we have the number of questions. Cool, so we've read input. All right. So now we want the majority for each one, I guess. It's probably smart. Maybe, yeah, okay, I'm gonna go to the bathroom. I'll be right back. Yeah, so I've decided it is easier to think about, especially in the two-person case, if we consider not being in the majority or not, but being with the, like, whether the first person got it right or not. So we're going to categorize the problems by either everyone agrees or first and second person disagree and the first and third agree, first and third disagree, first and second agree, first and third disagree, first and second disagree. So those are 4 types of problems. We want to know the counts of each type of problem. And then we want to brute force for the ones that are most common. We want to say yeah, I guess for everything except the ones that are most common, which is messy, we want to say how many did the first person get right? We brute force that for each type. So worst case, it's 30, 30, and 30. The last one's forced. Okay, so the runtime, I guess let's just map this out. Okay, so count how many of each of the 4 types of problems we have. Then once we do that, we have 30 times 30 I guess we want to like brute force all of the possible quiz types. That correspond to the given answers. Some n choose k stuff to count how many ways to make each of those quizzes. That should be order 1. It's a very odd spelling of the word quizzes. Interesting. All right, then for each of those, we need to evaluate how many. Okay, we want to evaluate expected score for each of the 16 strategies. So this is going to be 30 to the third times 16 times t. How big is this number? Eight seconds. Can we fit a times 30 on top? Probably not. Probably not. However, if they do 40 to the third, we are still small enough. That's 20 seconds. Nice. 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 So we don't, okay, so we'll make this 40 to the third. We'll take a hit there. Oh no, but we have big integers. Oh no. Okay, well maybe we will cross our fingers and hope data is random. Yeah. Yeah, that sounds reasonable. Big integers. That is super annoying. Yeah, okay. All right, yeah, we'll just do it, and then at the end we'll try and fix it, I guess, if we need to. Okay, how many of each of the 4 types of problems we have? right, so if we have, can we always have one person? That's kind of silly anyway. All right, so if n people is greater than or equal to 2 and responses at 0 I is not equal to responses at 1 I, then ID plus plus. Okay, it's greater than or equal to 3. And these two are different. Plus equals 2. And increment it. Cool. So now we have the counts of each type of problem. Good. All right. How many combinations of each type of quiz? Yeah. All right. Cool. So we can optimize this a bit to only include, or like to skip the most costly. Which type would be easiest to code to skip? Probably the one where everyone's the same, right? Yeah, that's easiest. So, okay. We can do that. We'll do that later if we need to. So we know, or like, we can easily tell the answer for responses at, okay, for type at 0. Okay, and type 3, count of type 3, and type 3 plus plus. All right, so person 1 needs to get, all right, so yeah. So if n type 1 plus n type 2 plus n type 3 is greater than n person got right at 0, then we just continue. Because, yeah, okay. Otherwise, int n type 0 will be n person got right at 0 minus n type 1 minus n type 2 minus n type 3. So now we know how many there are of each type. Okay. Let's validate that. So if n type 0 is greater than count of type 0, continue. Okay, so we now know how many questions of each type person 0 got 1. Person 0 got right. Good. All right, so person 2 score is going to be n type 2 plus person 0 gets, or they get things of type 0. Person 2 gets wait, this is kind of confusing. Yeah, okay. So we should probably just make a score method, static int score. Yep, let's do this. Okay. Wait, you want to maximize the expected number, right? Maximum expected score. Okay. So we want int agree mask int n type 1, n type 2, n type 3, n type 0. Let's put this first actually. What else do we need? We also need count, or yeah, array count of type. And we could pre-comp this, right? No. Wouldn't be very fast anyway. Okay, res equals 0. Okay, so the green mask, okay, so this is 1, 2, 3, 1, 2, 3. Okay, so we need the agree mask person 2. When does this person agree? So that would be do they agree with type 0? Yes. Do they agree with type 1? What is type 1? Type 1, they don't agree with. So that would be 0 left shift 1. Type 2, they do agree with. And then type 3, they don't agree with. We also need person 3. They do agree with this. The second one, they also agree. This one they don't agree. This one they don't agree. Okay. Okay. Int yeah, okay, so if n people is greater than or equal to 2, int person 2 score will be score, what is the agree mask? Agree mask person 2, and type 0, and type 1, and type 2, and type 3, and then count of type. How much time? 45 minutes. We should probably be fine, assuming there are no bugs. It's kind of crazy assumption, but all right. If person 2 score is not equal to score for person, what did I call it earlier? N person got right, at index 1, then continue. All right. If n people is greater than or equal to 3, we need person 3 score. It's the agree mask for person 3. It's not equal to this. Continue. Okay. So now we know it's valid. So this might have actually happened. Now we need to know how many ways might this have happened. So how many? Well, this is okay. We can probably be a little slow here because this should cut out most of the time. Yeah, so we probably don't need to be too worried about this. Good. So do we need a fraction? Maybe this is not quick. I would like to just rename the big integer. Anyway, I'll just type it out. Okay. Dot n equals n, or okay, big integer GCD equals n dot GCD with d. This dot n equals n dot divide by GCD. This dot d equals d dot divide by GCD. All right, how do you add two fractions? So you have a d over, or n over d plus o dot n over o dot d, which is equal to n times o dot d plus o dot n times d over d times O dot d, right? You multiply by this on your side, you multiply by this on their side. Yep, okay. N dot multiply O dot d dot add O dot n dot multiply by d dot divide, oh, comma, d dot multiply O dot d. Yuck. Yuckaroony. Good. Okay, now we need to compare. Right, we need to add, multiply, compare. Probably subtract. Well, let's just do compare. Public int compare to big frac O. Okay, A or N over D, and then we have O dot N over O dot D. So what we would normally do is do O dot or N times O dot D on one side, and then we would have O dot N times D on the other. Big integer me equals N dot multiply O dot D. Big integer him equals O dot N dot multiply by D. Turn me dot compare to him. Okay, we can optimize that out a bit if we need to. All right, so now we need number of ways. We need n choose k. Yeah, okay. Static, how much time? Big integer n choose k. N into k. We need to pre-comp this. Yes. Static big integer double array n choose k pre-comp. New big integer 5,000 is too big. 1,000 is probably too big. 500 should be fine. Let's do 300. 300 by 300. I think that should be fine. Shouldn't have any worries there. If n choose k pre-comp at n k is not equal to null, turn n choose k pre-comp at n k. All right, what else can we do? So n choose k. How do you do n choose k? If n is equal to 0, return big integer dot 1. Okay, what if k is equal to 0? K is equal to 0, do that. What if n is equal to k? If n is less than, or if n is greater, wait, if n is less than k. If you have fewer things, then you need to pick return 0. Yeah, it's going to be impossible. Otherwise, return n choose k pre-comp at nk equals n choose k minus 1, k minus 1, plus n choose k, n minus 1, k. Either pick this thing or don't. Good. Okay, so I think that's everything we need. All right, how do we do this? So now we need, how many ways did this happen? What a variable name, right? Okay, so we need n choose k. N choose k. How many things? N type 0. That's how many we got. What is n? N is count of type 0. Choose this. Dot multiply. Boom. keep her moving. N, choose K. Count of type 1. Choose N type 1. Good, yes, okay. What's going on here? Multiply. Don't mind me. This is just going to be absolute cancer, but we're fine with that, right? I thought so. N, choose K. Multiply by this. Boom. Type 2. Type 2. Okay. Yeah, I think that's right. I think that should be fine. So that's how many ways we could actually get this score. Yes, okay. All right, amazing. Good, good. Now, all we need is to evaluate every other score here. There are 16 possible scores. We don't even need big fraction. Why did I bother with the big fraction? Okay, big integer total correct, or total ways equals big integer dot 0. So this is a legit thing that might happen. Yeah, so total ways equals total ways dot add ways this could have happened. Okay, big integer array scores for mask is new big integer array. Should be 4. Yeah, yep, okay, so now we just, we're getting there, we're getting there. Should take, I don't know, another 10 minutes maybe. So we have the scores for each mask, okay. Yeah. Score. The green mask is mask, n type 0, n type 1, n type 2, n type 3, and the counts of type, count of type. Okay. So that's the score. So we get some score. Could have happened a bunch of ways. Big integer to add. Okay, yeah. To add is ways this could have happened. Dot multiply by the score for mask. All right, good. We have each of those. Now, score for mask at mask will score for mask at mask dot add. So now we have the scores for each of the masks. Okay. So now, get best. We've done that. Okay. So now we need to get and evaluate the best score. this thing compared to scores for mask at best mask. If this is greater than 0, best mask equals I. Okay. I guess we'll use it, but we don't need it. Big frac equals new big frac. The numerator, scores for mask at best mask. The denominator is total ways. Okay. Yeah, cool. So we have this fraction. Let's see if it works. And it should be pretty easy to convert, actually. Oh my goodness. Oh my goodness. Ooh. I am a genius. 2.9. Oh my goodness. I am so amazing. Oh, that was a pain, but we've got it. All right. Okay. So now we know the best thing to do. So we print what it is. Okay. Yeah. All right. "16 masks. Agree with the person on type 0. Yeah, okay, so let's say int array type for question. So we have the type for each question. We have whether the person agrees with person 0 for each question. That's in the mask. For each type. Okay. Gotcha. All right. String builder what I think equals new string builder. I is less than. What is I less than? We go up to number of questions. Boolean agree. Okay, so int question type will be type of question at I. Boolean agree with person 0 or person 1. This is if we have a 1 in this bit, yeah, if we have a 1 in our mask in this bit. Okay. So how do we check that? If best mask and 1 to the Q type, this is not equal to 0. Okay. Care. Okay, so if what is this called? Responses 0 I equals true. Me equals agree with P1. If we do, say true, otherwise say false. Else me equals agree with P1 false, otherwise say true. There's got to be a cleaner way of doing that. Okay, best answer dot append me. Thank you, and then plus me plus a space plus the fraction. Oh, this is the best answer, I mean. FFT, 3 out of 1. FFT, 2 out of 1. Some stuff, 4 out of 1. True, true, 4 out of 1. Do they have other examples? There are other answers that achieve a score of 4. Do we get the second half right? FFT. I don't know, I feel like maybe this is just a submit. Do these match? Oh my goodness, do these match? That would be cool. Looks promising. Looks like they match. I don't know, from a quick spot check. Yeah, all right. Let's not get a compile time error. All right. Oh. 1000th place. Yeah, the real question is, will I TLE? Should we go through the effort of, do I feel like it? All right, what would the optimizations entail here? I don't know. I feel like we're probably fine. I feel like I just don't want to worry about it. Yeah. I don't know. What place am I in? 755th. How many people advance? Oh, 15, yeah, okay. Yeah, so I'm not gonna worry about optimization. I think I've got the idea going here. So let's do solutions to them. All right, fun contest. Are we still recording here? Cool. So here's the idea, append sort. Yeah, so I guess maybe what do I think about the problems first? Append sort, I don't know. I thought it was just kind of ugly. I didn't really like it that much. Like, it works, I guess, as a problem. It's just kind of, I didn't really like it. Like, I solved it, but I didn't enjoy solving it. This one was kind of cool. Yeah, prime time. That was kind of cool, actually. I thought this was an interesting problem. I thought it was kind of cool. And then hack exam. Yeah, I guess it was maybe cool. It was really ugly, if the implementation is clean, then maybe I like it. But yeah, the fact that it required big integers was a little undesirable. I guess there's not really any getting around it. Yeah. So I don't know. Maybe it's fine. I guess it was a cool enough problem. Sure, whatever. Anyway, how do you do them? Solutions. So append sort. Yeah, this one's pretty easy. The observation here is for the first number, right? If you're looking at some suffix of these numbers, then whatever the first number is, you can only increase these numbers by adding digits. Wait a minute, can anything be negative? Yeah, okay, they're all positive, good. So since everything's positive, you can only increase the numbers by adding digits. And the side effect there is that you want the first number to be as small as possible. So the first number is going to be just what it is normally. For the rest of the numbers, you can add digits to them. But when you do that, you want to make the second number be as small as possible with the number of digits that you add. So if you can do it adding 3 digits, and you can reach the numbers 750, or you can reach 999, it's better to reach 750 than 999 because 750 will be smaller, and that might mean in the future you might be able to reach some other 3-digit number that you could, if it's somewhere between 751 and 999, right? Those are options that you would remove from yourself if you had picked a bigger first number. So yeah, so basically the idea is the first number stays the same. Then you want the second number to hit the smallest number it can by adding digits to the end, which is bigger than the first number. And basically you just have to case that out. So you should be able to see that's the idea right away. Once you know that's what you have to do, it's just a matter of going through all of the cases and not missing anything. I think I did that correctly. So what are the cases? Like basically, yeah, you're just going to go through the array. I used big integers because I don't know how big these things can get. Probably, well, they can probably, yeah, they can probably get pretty big. They can probably get to be 100 digits long, I think. So either do this with strings or with big integers. But the idea is the first number is going to stay the same. And then for the rest of the numbers, you need to have something bigger, which is the first biggest thing you can get by adding digits to this number in order to get something bigger than the previous number. So I did some method here, which gives me the next biggest number you can get by adding digits to the end. Let's look at that. Okay, so first of all, if our number is already bigger than that last thing, we won't add anything. We'll just return ourselves right away. That's this case. Otherwise, in the rest of this assumes we are smaller than or equal to the previous number. So we have to add at least something. Now, if we just add all 9s, if that still has us smaller than or equal to it, that means that we need to have one more digit than him. For instance, let's say we are 1,000 and he is 2,000, right? If you add, or we're the number 10, he's 2,000. So if you have, let's do an example here. You have 10, and then the previous one which we have to beat was 2,000. We can add 9s to these columns here. We can put a 9 here and a 9 here, but we still won't beat the 2,000. So if that's the case, we have to get one more digit. We want to do that by adding zeros until we have the next digit. This is the same if this is 10, but it could be like 19, right? Or like let's make it like 17. So it's, in this case, it's 17 with 3 zeros. That's the smallest number we can get. Because if adding all 9s doesn't work, the next smallest thing is adding all zeros, but one more zero. So there's the choice there. And then if it does work, then you do more casework. So the TLDR on that is if you are a prefix of him, then you take his suffix plus 1. If you're not a prefix of him, and that means you have to be bigger than him in order to get to this state. If that's the case, then add all zeros. Yeah, so it's kind of messy, not super clean, but I guess you just have to case work it out. That's why I guess I didn't really like the problem, because this is not just like kind of gross, but maybe there's a better way of doing it. I don't really know. Yeah, that's problem A, append sort. You see what to do really quick. Actually doing it is kind of annoying. Okay, prime time. So in this problem, you have a bunch of prime numbers, which is an important restriction in my solution at least. You have a stack of cards, a bunch of prime numbers, and all of the prime numbers are relatively small. They're all between 2 and 499. Okay, so the next thing is what you want to do is separate these into two different stacks. One stack, you'll add all of the numbers together. The other stack, you'll multiply them together. You want the sum of your left stack to be equal to the product of the right stack, and you want whatever that sum equals to the product, whatever that winds up being, you want that to be as big as possible. And that's the goal. So the thing to notice here is that if you have a bunch of prime numbers that are all bigger than 1, I guess all prime numbers are bigger than 1, right? But if you multiply a bunch of numbers bigger than 1 together, if you start multiplying a lot of numbers, you'll get a very, very big product really quickly. So the sum will stay relatively small. In fact, my hypothesis is if the sum ever gets bigger than 3,000, the product will be bigger than 10 to the 15, right? There are no ways of finding prime numbers which add to a number bigger than 3,000 and multiply to a number smaller than 10 to the 15 if you're only using primes less than 500. I think the best you can do is using 499 a bunch and then using one more prime until you have like just barely underneath the sum. Then the product you'll get it'll be too big, right? So yeah, I don't think it's possible to do that. What that means is there are only 3,000 different sums that we need to check. We know there are only 3,000 sums that we need to check, because basically the sum won't change. The sum of the pile that we're adding will basically be all of the cards. And then we remove sum total from this. The total we remove is up to 3,000, but it's going to be a relatively small number, somewhere between 0 and 3,000. So we can brute force the size that we remove. If we know the size we remove, we know what the product of the other group has to be. So we know the product of this group because we know how many we remove. Now if we know the product and we know we have a bunch of numbers that need to multiply up to it, and we know all the numbers are prime, we can figure out what numbers should be in that group, right? So if it's 12, we need 2 2s in that group and 1 3, because 2 times 2 times 3 is equal to 12. And yeah, after that it's just implementation details. So you just have to not miss any cases. Just kind of the theme of this contest and maybe CodeJam in general. Don't miss cases. So in particular, we're going to brute force the product side sum. This goes up to 3,000, I guess 6,000 maybe, but something small. And once we know what this sum is, we know the sum of everything else. That's going to be the sum of all of the cards minus the product side sum. That's like what the other stack needs to add up to. This is remaining sum. So that's what the other side is going to add up to. That's also equal to what our product needs to be. They need to match. And then we just do some stuff with that. We iterate through all of the primes that we're given, and we take it out as many times as we can. We make sure the number we multiply to on the multiply side is equal to 1, and we make sure the number we add to is equal to the thing on the other side. If that's the case, this is some possible answer. The runtime of this is 6,000 times log plus 6,000 times the number of factors they give us, which is 100. So it's like pretty quick, like 6 times 10 to the 4 per test case, 100 test cases. All right, hopefully that made sense. It was a bit messy to explain, but I think I did my best there. The last problem is hacked exam. So in this problem, you have 1, 2, or 3 students who take some exam. You're given what they answered, and you're also given their final score. But you want to take the exam yourself, seeing these submissions and their score, and you want to score as well as possible. the question is, how do you do it? And also, if you do that, what is your expected score? So they give you an example. If you're trying to solve this third test case, your expected score might be a very big unruly fraction that you need to use either big integer for, maybe int 128, maybe Python, something kind of messy. So yeah, I think int 128 should be fine, but it's going to get messy. So be careful, I guess. All right, so here's the idea. For each question, you have 3 pieces of information. You have what person A answered, what person B answered, and what person C answered. Really, it doesn't quite matter what person A answered, because you can, like, if person A said false, you can just invert everyone's answer. So you can kind of look at the problem as if person A answered true for everything. So rather than looking at the problem as like, what did people mark true or false on their paper? Mark down, did these people agree with person 1 or not? Right? So person 2 might agree with person 1 and they might not. If you look at the problem like that, there are 4 types of problems, assuming there are 3 people. So there's person A says true for each of these types. This is like person 1. Then we have person 2, and then we have person 3. So person 2 might agree, and person 3 might also agree with person 1. Person 2 might disagree, and person 3 might agree. Person 3 might agree, person 2 might, or yeah, like this, and there's also false, false. So these are the 4 options. You get these 4 types of questions. Now, what's important is we don't really care the order of the questions. We only care how many of each question there were. We know the total number of questions is up to 120. So we can brute force, let's say we brute force this, we brute force this, and we brute force this. At the end of the day, we know how many questions each person gets right. So we know, like, okay, I'm saying brute force, but it's a bit messy here. So like, yeah, we have these 4 different types of questions, and we want to see how, like, in what ways can the real answer key, give each person the score they actually got, right? So maybe person 1 scored 10 points, person 2 scored 5 points, person 3 scored 12 points on an 18 question quiz. The question is, like, in what ways can the actual score match the score people received? And what we're going to do is, like, first count how many ways is this possible, and second, we're going to count for any possible strategy we have, what would that score give us? Now, that's a bit messy. If instead of doing that, all you want to do is solve parts 1 and 2 of this problem, that's kind of much easier. You still have to do the evaluation, but in order to solve parts 1 and 2, you can just do a DP, and your DP would store, like, what index are you on, what score of person 1, what score of person 2, what's your score. That should work fine for this, and you can optimize it a bit for your score. You can figure out your score on the fly. But you just want to say, agree with the person who gets the most questions right, if you only have 2 people. If you have 3 people, that strategy doesn't work anymore. But, like, if you agree with the person who gets the most questions right, you'll have the right strategy there. Now, there's one caveat there, which is if someone gets over half of the questions wrong, you want to invert all of their answers and also their score, right? So if someone gets every question except 1 wrong, then you want to say, okay, actually, when they said false, they should have said true, and they should have gotten every question but 1 right. So that's the strategy there. That will get you anything with n equals 2, and in all of those cases, your answer will just be an integer. I don't have a proof for that. It's just kind of intuition. But for test case 3, you got to do some very complicated, messy stuff. And I'm explaining it here. So yeah, let's finish this explanation. So there are 4 types of problems. What we're going to do is brute force the type of answer that actually happened, and the type of answer will have, for some number of each questions, how many the first player got right. So we're going to know for each of these types how many player 1 got right, or person 1 got right. If we know how many person 1 got right, we know how many person 2 and person 3 also got right. Okay, so then we can verify if there are maybe 10 of these questions, 15 of these questions, 2 of these questions, and 1 of these types of questions. If this is the number person 1 got right, so person 1 got 10 of the first type right, 15 of the second type, 2 of the third type, and 1 of the fourth type, and maybe total there were 12, 10 of the 12 of these, 15 of the 18 of these, 2 out of the 10 of these, and 1 out of the 15 of these. So we're going to brute force these numbers on the bottom. Then we can figure out how many points everyone else would get. So person 2 agrees with person 1, so they would also get 10 points for this first question. Person 3 would as well. For the second one, person 2 disagrees with person 1, so every time person 1 got it right, person 2 would get it wrong and vice versa. So person 2 would get 3 points for these types of questions if this happened. Now we're going to brute force this, and we can do this by brute forcing these 3 values and then figuring out what this would be with math. Oh no. Wait a minute. Oh no. No, I'm fine. Okay, never mind. All good. Yeah. I thought I was gonna TLE. I might still TLE, who knows, but I think I'm actually fine. Yeah, so we brute force what these 3 things are. Worst case, there are 40 of each. And then our runtime here is 40 times 40 times 40. This is pretty easy to do because we know person 1's score has to equal this final thing, right? So we know how many points they get from each of these 3 things. We can figure out how many points they need to get from the question 1 type, which means we can figure out this needs to be a 10 here, given the other ones are 15, 2, and 1, because person 1 has to get a total of 10 plus 15 plus 2 plus 1, which is 28, I think. Person 1 has to get 28 points right on their quiz because they got a score of 28. We were given that an input. Okay, cool. So we've made a lot of progress here. So we're going to iterate through, we're going to brute force what these bottom 4 numbers are. Once we know what these 4 numbers are, we know how many different types of quizzes there are that are of this type. We can do that with n choose k. So there are 12 questions. We get 10 of them right. There are 12 choose 10 ways of doing that. Same thing here. We do some multiplication here, some multiplication here. So we know maybe there are like a billion quizzes of this type, for instance. I don't actually know, but you can do the math with n choose k. Now, once you have that, it's a very long problem. Okay, we're going to say, in total, there are only 4 different types of questions. For 2 questions of the same type, we have no way of distinguishing them in input. So it doesn't make any sense for 2 questions of the same type to answer the first one in one way and the second one in a different way. Which means there are only 16 possible strategies here. For each of the 4 questions, for each of the 4 question types, we should either answer them in the same way person 1 does or in the opposite way person 1 does. Right? Like, it doesn't make sense to do anything else because we have no way of distinguishing them apart. So if we're going to do that, there are only 16 possible strategies that make any sense at all. And we can just say for each of the 16 possible strategies, what score would that strategy yield? And then just take the best one at the end and then simulate it. Okay, blah, 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 blah. Here is the code for that. Very messy. So, yeah, this is kind of difficult to explain, but we get the responses and how many each person gets right. Here are how many of each types of questions there are, with some math, some bit math shenanigans going on here. Person 2 will agree with certain questions, not with other ones, depending on these bit masks. And then I store the score for each of the possible strategies. There are 2 to the 16 strategies because there are 4 types of questions. So for each of those 4 types, you should either agree with person 1 or not agree with them. Then we do some n choose k stuff. We validate that this is like the brute force part, right? So we do the brute force in 40 cubed time. We make sure it's like legit, kind of, and then we do some n choose k stuff, and then we evaluate the score for each of the possible strategies, and at the end we pick the best strategy and print it. That's very high level, but going into this would be very difficult, and no one really wants to watch that anyway. So we're not going to do that. All right, we have a minute 16 seconds left. I think I'm just going to stall here so we can see how we did. But yeah. I don't know. I'm not too worried. I feel like I'm fairly confident in the solutions, and I just have to get in the top 1,000. And I think there are probably a lot of people who just got this easy part. Probably a decent proportion of people. Like given that you have 33% of people aren't solving a pen sort 2. I don't really know how, but yeah, given that that's the case, there are probably a decent number of people who just get the 8 points on this. So, cool. Master Coleman. Well done. Oh my goodness, did I beat Tourist? Ho! I may have beaten Tourist. Ladies and gentlemen, is this the greatest day of my career? Pow, pow, pow. I beat Tourist! 27th place! Yeet! Tourist got it wrong. That's unfortunate. I'm sorry, man. Well, I'm sorry. I feel bad for gloating now. Oh. Well, he made it. Better luck next time. I think he's won this like 7 years in a row, right? So I feel kind of bad, but also like, yeah. It's an understandably annoying problem. So it's fair. GG to everyone who competed. I hope you enjoyed. I had a fun contest. Looks like most of my friends, Raidwush, I guess, just did not like the contest. He's like, nope, I'll do the next one, I guess. Maybe he got tired. Maybe it's too early in Poland or something. Yeah, 27th place. I'm happy with it. I guess it doesn't really matter, right? So, yeah. I kind of went harder than I needed to go, but fun contest. A was dumb. B and C were pretty cool problems. Pretty fun. Okay, that's all. Hope you enjoyed. That's all from me. I had fun. Good luck, have fun up solving. If you made it, I'll see you in round 2. We'll be fighting for a t-shirt for sure, because that's the thing you do on CodeJam. You fight for a t-shirt. And if you didn't make it, good luck, have fun on round 1B. You got another chance, and don't worry, Tourist and I won't be there breathing down your neck. So you'll have his spot, you'll have my spot, you'll have Ben Q's spot too, Umnik's spot too even. First place Umnik, nice win. So yeah, you've got round 1B, and even if you don't make 1B, you still have round 1C, so you got lots of chances. Of course, upsolving is a great thing to do, especially with these annoying problems. It helps your implementation, which is going to be important in CodeJam. And yeah, there you go. Best way to practice for contests is do problems written by the same authors. So here's a good contest for them. All right, that's all from me. Hope you have a great day. Hope you enjoyed the contest. See you soon. Tomorrow morning for the Code Forces round, I guess. Goodbye.